All right, so we'll get started for today. I think that's too loud. Okay. All right, so I think we'll get started for today. So over the last couple of lectures, we have been looking at network layer. And these are the sort of things we wanted to cover here. We wanted to get an overview of the network layer and get a feel about the services it provides. And then we wanted to look inside a router. And then we get into one of the actual network layer protocols, which is IP. And then we look at routing protocols, right? So I think today we'll be able to finish off this part of the of the syllabus. And then I think I guess we have covered everything except for here, routing protocols. So we'll look at routing protocols today. And we'll also do tutorial 2 today, okay? So we'll do that. That's the plan. All right, so in the previous lectures, you have looked at what are the things that network layer provides. Basically, network layer is responsible for making sure your data is routed from the source to the destination through the routers in the network. And there are two basic functions that the network layer is supposed to provide you. One is forwarding, the other is routing, right? So forwarding is the process when a packet comes in any one particular interface of the router, and you decide that it has to go out from another interface. So forwarding is the process of moving the packet from the input link to the output link, right? And routing is the process of deciding what is the output link I should take. If I have 6 different choices, which is the best of these that I need to pick, right? And previously we have also divided these two functions in either as the data plane or the control plane. So the forwarding is the job of the forwarding is the job of the data plane, and the routing, which decides which path to take, that's the job of the control plane. And we have also looked at how there are 2 ways in which we can implement the control plane. One is to have the routing algorithm run at each individual router, and in the more recent version, or the recent way of doing things, in which you have one central remote controller that decides or determines the routes for all the routers, the forwarding table for all the routers, and then pushes it down to the routers themselves. We have also looked at the architecture for a typical router, and here again we can separate the control plane and the forwarding plane. So the control plane consists of the routing processor, and in the forwarding plane you have the input ports, the switching fabric, and the output ports. All right. And then we also looked at how we can organize our forwarding table so that we don't have to have billions of entries in the forwarding table, one for each destination address. And the way we do this is by hoping that maybe we can group IP addresses together. So a bunch of IP addresses, I can just have one entry saying you need to go this way. And last time when we were talking about subnets, that was why we do it this way. Okay. All right. And last lecture specifically, we looked at different network layer protocols, and we focused mainly on IP, and we looked at the format of an IP packet, what the different headers mean, and then we got into IP addressing. And here we talked about subnets, and a subnet is formed if you disconnect the interface, and all the hosts that can talk to each other without having to go through another router, they will form a subnet. And inside a subnet, the first so many bits of the IP address will be the same for all the hosts, and last few bits will be used to distinguish between individual interfaces within the subnet. So here I think we had a bit of towards the end, a lot of you came up to me and then you were asking about subnet masks, right? So let's talk a little bit about this subnet mask, right? So an IP address, IP version 4 address is 32 bits, right? And what we say is that the first few bits of the IP address, a certain number of bits of the IP address will be constant for all the hosts or all the interfaces within the subnet. And this is called the subnet ID. And the last few bits, which vary between every interface, those are the host ID kind of thing. Right? So let's talk about how we can. So if I look at this particular example, on the subnet on the top, it says 223.1.1.0/24. That's the subnet mask. Well, that's the subnet ID, sorry. That's the subnet ID. And what it says is, it's a /24 subnet. So what that means is, if you get a 32-bit IP address belonging to this subnet, the first 24 bits are the subnet ID, and the remaining 8 bits are your host ID. And that's what it means. So let me go again here. No, this one. So one of the examples here was 223.1.1.1. And what we are saying is, this is a /24 network, which means that if I were to expand these out into binary digits, binary numbers, so 223, let's try and do that. I will have to Google or ask my machine to do this. Let's see, Google 223 to binary. Oh yeah, that's 1101111. The next one is just, that one is easy, I can do myself. That's a 1. That's a 1. That's a 1. Right? So I have blown up the IP address in the dotted decimal format to the binary format. So a /24 address means you pick the first 24 bits. This is your subnet part of the address. And then the remaining part is the host part. So in this particular subnet, every computer or every interface, this part will be constant. So only this part can change. So here you can have 2 to the 8 different possibilities. Right? So in this particular subnet, you can have roughly 256 different interfaces. What if I needed more computers in this? So then you have to say, oh, I will only consider the first 23 bits as the subnet, and I'm going to leave 9 bits for the host. So now you can do 2 to the 9, which is 512. Okay? And last time I was also giving you an example from my machine. It takes so long to. Yeah. All right. So if you look here, it says my IP address is this 172.24.231.64, right? And it also says that my subnet mask is 255 to 192.0. 255, 192.0. So what is the subnet mask? What I do is, if I take the subnet mask and I apply it on the IP address, I will get the subnet ID. So basically the subnet, by looking at the subnet mask, I can tell how many bits are going to be used for the subnet part and how many bits are going to be used for the host part. How can I do that? Let's look at this, right? So this is 255, come on. Yeah. So this was our subnet mask. Right? So again, let's convert it to decimal. 255, sorry, binary. 255 is all ones. This is also all ones. And now this one is 192. And this time I have checked, I think this is just 2 ones. Right, so this is my subnet mask. So if I look at this, the first 16 plus 2, 18 bits. Let me double check if that is 192 decimal or not. 192 to binary. Yeah, that's correct. So here I have 16 plus 2, 18 bits, which are 1. So this one essentially is a /18 network, /18 subnet. So the first 18 bits are going to be used as the subnet ID, and the remaining 8 plus 6 is 14. So this 14 bits, this will be for the host. So in this case, we can have 2 to the 14 different hosts in this particular subnet where we are at right now. Okay, and if you were to ask, all right, fine, all good, what is my subnet ID? What is the subnet ID of this particular network? So what you're going to do is, this 172.24.231, this is my IP address, right? Blow it up into binary. Let's do that. And how much is it? 172. So this is going to be 10, 10, 11, 00. This is 172. Then 24. I should be able to do 24, but still. Three zeros, 1, 1, and then 3 zeros, and then 231. That I can't do. 3 ones, 2 zeros, 3 ones. And then 64, that one I know, but sorry. The one should be here. Right. So this is 24. This is 231, this is 64. Do a logical AND operation between them. So if you do a logical AND operation, you will basically be left with zeros on all this side. Right? And here, whatever is at the bottom, that's what you'll end up with. So this is still 172, this is 24, and this is how much? 64 plus 32, right? No, 128 plus 32, which is how much? 64, 192, 128. So our subnet ID here is still this. Okay. It's not necessary that subnet mask and subnet ID will always end up to be the same. In this case, it just happens to be that way. You know, if my IP address here had a 0, then I wouldn't get the same. But the idea is that if you look at the subnet mask, you blow it up, you see how many ones are there. And the way your subnet mask will be, you will never get something like this. Subnet mask will always be a sequence of continuous ones followed by zeros. By looking at how many ones are there, you know how many bits you're going to use for the subnet, how many bits you're going to use for the host. Usually when we say the /24/18, that's for us humans to be able to, I can just quickly tell you this is a /18 network. And you already know, okay, first 18 bits are going to be this. But when you encode this in a computer, it's very difficult for a computer to say, oh, you /18. Rather, you give it a sequence of zeros and ones. So when you tell a computer what's the subnet mask, you write it in the form of 255, 255, 192, 0. Questions? All right, so I thought I'll just talk about that a bit because last time there were a few questions, and so I hope this is better and not worse than before. Okay, so last time we talked about these subnets and how we create a subnet and what's the meaning of a subnet mask and so on. Come on. Yeah. And then we talked about the protocol DHCP, which is used for, so DHCP is a very useful protocol, and it's used for assigning IP addresses to hosts. And this is quite useful because in a scenario like this, when you come in, you can directly talk to a DHCP server and you're automatically assigned an IP address. And when you leave, the IP address can be reused for somebody else. Right? And last time we looked at how DHCP works. It's basically a sequence of 4 interactions. First, when a new client comes in and wants an IP address, it sends out a broadcast aimed at DHCP servers asking for help. And any DHCP server which gets this message broadcasts back a reply with some offers of IP addresses. Then the host will pick one of those IP addresses and formally request for that particular IP address. And once it gets a confirmation back from the DHCP server, you officially have that IP address with you. And usually there's a timestamp associated with every IP address which comes from DHCP servers. Once that time is over, you have to refresh or it will be given up to somebody else. All right. And then the last thing we saw on Wednesday was IPv6, and we saw that there are 2 motivations for IPv6. One is we ran out of IP addresses already with IPv4, and then to make the life easier to make processing easier and faster at the routers, there were certain things done. For example, we made the header length fixed at 40. We don't allow any fragmentation, and we also dropped the header checksum from so that you don't have to recompute the checksum for every packet you get. And then last thing we saw last time was that when you have a mix of IPv4 and IPv6 routers, in order for things to coexist, what we do is we encapsulate IPv6 packets into IPv4 packets to traverse the IPv4 routers. All right, so this is sort of what we had done last time, and maybe we stop there. Okay. So now let's come to the new stuff, which is about routing protocols. So basically the goal of the routing protocol is to find the best path to a destination. You tell me that I want to go to this particular destination, and I should be able to tell you, okay, first you go here, then you go here, and then you go here. Right? I should give you the sequence of routers you need to follow to get to the destination. And when I say the best path or a good path, you could define what it means to you to be a best or a good, right? So for example, we could say, there may be some cost associated with every router you visit. Because you may, from Singtel, I may go to some other ISP, global ISP or a regional ISP and so on, and they may charge me different amounts of money based on how much data I give them. So it could be based on actual dollar kind of cost, or it could be based on, the shortest path, the least number of routers I need to visit. It could also be, you could define your best in terms of congestion. Which is the path which is least congested? Even though it may be a little longer, I don't care. I would rather go through there. Right? So you could define in any way. And routing has been and still continues to be one of the most challenging networking problems. And there's still a lot of people who like to work on routing related problems. Right? So let's talk about these routing protocols a bit. But before we get in there, the way we will address this, it's convenient to think of routing problems if you consider your network to be a graph. Okay? So in this particular graph, we can represent it as a set N and E, where N is the set of nodes or vertices. So these are basically the routers in your network. Right? So your graph will consist of nodes or vertices, where each vertex is one router, and the links connecting each router forms the set of edges. If you take all the links, then you have a set of all the edges that you have in the network. Also, with every with every link or edge, you can associate a cost. Now this cost, you can define how you want to be. You can say, this is the money I charge if you use this link. Right? This is $5 per MB or something like that. Or this could be based on the actual distance. How long is this cable? Longer the cable, you can have, you increase the cost. This could be based on the level of congestion right now. So cost doesn't have to be static or fixed. Your cost can vary over time. And if your cost varies over time, you need to run your routing algorithm every time the cost changes. Or in the very simple case, the cost of every link, you could just leave it as 1. So in that case, you would find the path with the least number of hops, right? That's what would happen if you use cost as 1. So now you may ask, Prof, what do we use in real life? What is the cost that we use in real life? Many times the cost, for example, inside NUS. If you are the network administrator here and you're responsible for the routing tables of all the routers within NUS, most likely you will just put cost to be 1. It doesn't really matter much. You just want to find the shortest path. Right? And in most cases, in real life, we just do that. We hardly make costs to be proportional to distance because, it's very difficult to measure distances. It's very difficult. We don't also want the cost to be proportional to congestion, for example, because congestion keeps changing frequently. And when that happens, you have to recompute your paths and so on. So nobody likes that. So in most cases, people would just say cost of each link is 1 and then try to compute the shortest path based on that. Right. So then, having said that, so the main question that we're asking is that, we have a graph. The graph has a set of nodes. It has a set of edges. And we have also assigned costs to each one of these edges or links. Now, when I go from a source to destination, let's say U and V, from U to Z, I am visiting a set of these links, right? So the cost of a path that I follow is the sum of the costs of each one of these links that I pass through. So it's an additive thing. So I say cost will be, so the total cost of a path is the sum of the cost of the links that I follow in that path. So in this case, the cost is 2 plus 3 plus 5, which is 10. Okay? And the routing algorithm, what it is trying to do is, it's trying to find the least cost. There are many possible ways for going from U to Z. Right? I just drew 3 here. There are many more. I want to find what is the least cost path from going from, let's say, U to Z, or from any host to any host. Or if I am a router, I want to find the least cost path from me to every other router in the network. That's very good. Now, before we get into the exact algorithms that we can use for doing this, there are many different versions or many different ways in which you can come to the answer to this question of finding the shortest path. For example, do we have global or decentralized information? So for example, if I say global, then this particular router U knows the topology of the entire network. It knows the entire graph. It knows that there is a U, V, X, Y, everything, and there are these links, and these are the cost of the links. That might be easy enough to do in a small network, but difficult to do in a large network, right? But things will be a bit quicker in this case. On the other hand, you can say decentralized. As a router, I don't know the rest of the world. I just know my immediate neighbors. I know I have 5 outgoing links, and these are the routers I'm connected to. So I only know my neighbors. Right? But even though I only exchange information with my neighbors, I still want to be able to find routes to every other node in the network, and these should be the best routes. So these are a little bit more challenging, but these sometimes are a bit more practical. Because in real life, it is difficult to find, it is difficult to get information about all the nodes in the network. However, when we come to the software-defined network, or the centralized one, when we looked at the control plane implementation, in one case, each router was responsible for finding its own forwarding table. Usually those would be decentralized. You would just talk to your neighboring routers and somehow figure out the route. However, in the second case, where there was a centralized controller finding the routes for everybody, that would be sort of like this, right? Where that guy had information about everybody in the network. And also you can break down your routing algorithm as either static or dynamic. In the case of static, you calculate the forwarding table once and you're done. Or you do it once a day or once a month, something like that. Your network doesn't change very often. And in the case of dynamic, you can say my routes change very quickly, so I need to recompute my paths. So most networks would still go with static. You don't change very often. Except in the case of wireless ad hoc networks, like, for example, imagine there's a group of soldiers, they're going out in the battlefield, but they have wireless connections between them. So there, things change very quickly. In those cases, you may want to, update your routing tables more frequently. But for most of the, civilian or commercially deployed networks, things don't change that quickly. All right. So now, there are many different routing algorithms which are possible. And in this module, we don't really care about going through all of them. And I just want to give you one routing protocol as an example, right? And try to learn. And the one that we are doing is a link state algorithm. And this falls in the category of global, right? Here each router is assumed to know everything about the network. So I know every other node and I know every other link. I know the cost of every other link in the network. And I want to find what is the best path from me to every other router in the network. So that's what we're going to do with Dijkstra's. So the network topology, the link cost, and so on, every node knows everything. Okay? And how can we do this in practice? One option is, I know who am I connected to, right? I am connected to 5 routers. These are my 5 links. These are the cost of the 5 links. I broadcast this. I send it to everybody. I send it to my neighbors. My neighbors will take this, they will send to their neighbors. Those neighbors will send to their neighbors, right? So at some point, everybody in the network will know. Of course, there's a lot of overhead involved here, and there's a lot of broadcasting and so on, but it will get the job done. Right. And all nodes have the same information. And what we will do is, we will compute the least cost path. Every router is running this, so that router will compute the least cost path to every other router. And the way this protocol works is it goes in iterations. How many iterations I will need? The number of iterations is equal to the number of nodes or routers in the network. And at the end of each iteration, I will find the shortest path to one new router. We'll see how that does. Now, before we get into the algorithm itself, there is some notation we will use. C of xy. This will be the cost of the link between x and y. Imagine you have two routers CXY. The cost is denoted by CXY. What if there is no link between x and y? Then the cost is infinity. So if I go here, the cost of the link between u and w is 5. What is the cost of the link between u and z? Infinity. There is no link between, there is no direct link between u and z. So the cost between u and z is infinity, but between u and w is 5. That's what it means. Okay. And we also maintain a variable d of v. So I am a router. I want to go to v. And I'm going through iterations, right? At every iteration, in this particular iteration, what is the current value of the cost from me to node v? That's what I'm denoting by dv. Okay? And in order to get to v, what is the previous node I need to visit? Usually I go by hop, right? So maybe from me, in order to go to v, I need to go through w, something like that. So what is the previous node in order to get to v? What is the one hop away from v? And I will also maintain a set denoted by n prime. And since every iteration I'm doing this, every iteration I will add a new node to this set. And this set denotes what are the routers for which I already know the best path. And at the end of my algorithm, this n prime will have all the routers. Initially it will have nothing. At the end it will have everybody. Okay. So let's take an example and let me go through the steps, and so hopefully all of this will make sense. Right. So let's look at the algorithm itself. It's called Dijkstra's algorithm after the person who invented it. And there are two things. We will first start with some initialization and then we will do iterations. So let's do the initialization first. We are looking at the whole thing from the point of view of router U. Okay? I am router U. I'm going to calculate this. So I'm initializing this. So n prime is the set, and this, the elements in the set denote I know the best route to you already. Initially, this only includes U. Why? I am node U. I don't need to go anywhere to get to U. So it's it's trivially known, right? Node U knows, no, we don't need to go anywhere. So fine. Now for every other node in the network, if that particular node, I have a direct link to that particular node, then the total cost of going to that particular node is I'm directly connected to you, so it's the cost of that link. Otherwise, the cost of going to that is infinity. Okay. Let me quickly jump here and show you what that initialization means. So here I have a network and we have different costs associated with different links. Let's look at the initialization. That's step number 0. We are looking at it from the perspective of node U. So initially n prime consists of node U. So let's see. I want to now initialize everything. What is the cost of going to V? I have a link going to V. So the cost of that is 7. And what is the predecessor node in order to go to V? Well, this is the node V, this is the link. On this end of the link we have U. So I can reach directly. How about W? Well, I have a link to W. Cost is 3. Predecessor node is U. For X, I have a link. The cost is 5. And the predecessor of that is U. How about Y? Is there a link between U and Y? No. So the cost is infinity. And there is no predecessor node. Similarly for Z, the cost is infinity. So this is the initialization part of things. Okay. So, written in better than my handwriting. Right? Okay, so this was initialization. So now let's go back to our algorithm here. Okay. So we have done the initialization. Now let's go into the iterative process. And we will go through a loop, and this loop will continue equal to the number of n minus 1. There are n nodes in the network. U is already done. So now I need to run it n minus 1 additional times to get the paths to the others. So this is what I do. We find one router, some router, which is not in n prime. So we don't know the path to that for that yet. So we need to find a node that is not in n prime, but the distance for that should be the lowest. Okay. And then we will add that to our set n prime. So from all the other nodes, I will pick the one with the least distance. And I will add it to my set n prime. And now, for everybody else, I'm going to update my knowledge of the distance from to them. How? I will check which is better, their original distance, or is it better that I first go to W and maybe there's a link from W to V. Okay? So pictorially this is happening. Okay, I'm U. There are many other nodes in the network. I pick amongst all of this which is the node for which my distance is the least amount of distance. So maybe this is the one with the least distance. Now I check. Let's say this is some node Z. Previously, the distance was TC. Is it better to keep this, or is it better that I first go to W and then go from W to Z? Which is better? If the original one was somehow shorter, I keep it. But if it is better I go to W and then from W to Z, then I know that I need to go through W to go to Z. That's their whole intuition. Okay. At every step, I will pick who is the best neighbor right now, or best way to go, and from there, is it any better? So let's take a look at this, and then. So I will update the distances for everybody, for every other node in the network. And I check if the new cost to V is either the old cost or the shortest path to W, and then from W to V. And I repeat it till all the nodes belong to N prime. So there's a loop going on here. Okay. So let's go back to our example, work through the example, and hopefully these steps will be clearer. Let me erase everything here. All right. So this was our example, and we had already done the initialization. So now we are in the iteration loop, and what we are supposed to pick, we are supposed to pick the node with the least cost. So here, these are my options. Which one do I pick? This is the one with the least cost. Right? So my N prime now becomes U and W. Okay? Now W is done. I don't need to worry about W anymore. I know in order to go to W, I have a direct link. The predecessor node is U. How about the rest? Previously, if I wanted to go to V, my cost was 7. And I was directly connected. The predecessor node was U. What if I go to W first and then go to V? So the previous cost is 7, but if I go to W, that's 3, and W to V is 3 plus 3, which is 6, which is better than before, right? So this one was 7, and this is 6. So now I pick the minimum, so of course going through W is better, right? So this one becomes 6, and then we should go through W here. Let's look at X. Sorry. Previously, the cost of going to X was 5, and we were directly connected. What if I go through W? If I go through W, this will be 3 plus 4, 7. The previous cost was 5. If I go through W, it's 7. So no point in changing. So this still stays at 5 comma U. How about Y? Previously the cost was infinity. Now if I go to W, and from W I go to Y, so that's 3 plus 8, 11. 11 is less than infinity, so I update it. How about Z? Previously the cost is infinity, but now I can go to W, but there is no link between W and Z. So this guy is going to stay at infinity. No change yet. Okay. So let's erase everything here. So we are done with our second iteration. Alright, sorry, this is the first iteration. Now we repeat. We don't know anything about V. We haven't yet found the shortest to V, X, Y, and Z. So I have 4 options. I again pick the one with the least. The one with the least cost is X. So now I become U, W, and X. And now I check. So don't need to worry about W, no need to worry about X. It's only about V, Y, and Z that I care about now. Okay. So previously, the best way to go to V was like this. Now, what if I go to X? It will cost me 5, but then there is no link between X and V. So this doesn't change. This will stay at 6. How about Y? Previously the cost of going to Y was 11 and through W. If I go via X, it will be 5. plus 7, which is 12. So going via W is still better. How about Z? Previously the cost was infinity, but now I can go to X, which is 5, and then there's a direct link, which is 9. So that is 14. Okay. So now I can update this. Now again repeat. Now I have three things, V, Y and Z. Which is the smallest? W is the smallest. Sorry, V is the smallest. So next time I will add V to my list. So now I don't need to worry about this guy, I don't need to worry about this guy, I don't need to worry about this guy. Okay? So now I check about Y and Z. So I will go to V first, like this, which is a cost of 6. Now, how about Y? There's a link between V and Y. That's 4. So the total cost of going to Y via V will be 3 plus 3, 6 plus 4, 10. So that's cheaper. So I should say this is 10 and we should go via V. Right? And now there is no link between V and Z, so this doesn't change at all. This will stay at 14x. And now I have two things to choose from. 10 is the smaller one. So next time I will add Y to my set n prime. And all these 4, I don't need to worry. I just see, okay, previously to go to Z, I go via X and the cost is 14. If I go via Y, right, the cost of going to Y is 10, and then there's a link between Y and Z, which is 12. So 10 plus 2, which is 12, which is less than 14. So I will say 12Y here. Okay. So that's 12Y. And now I have only one left, so of course I can just directly add it and nothing else needs to be done. Okay. So how would I find the path to any destination that I want? Basically you start with the destination and then you construct the path by tracing the predecessors. So let's take Z as an example. Right? I go to the table, it says the predecessor node is Y. So from here I should go to Y. Then I check the predecessor node for Y, it says V. So I should go here. Then I check the predecessor node for V, it says W. So I should go to W. Then I check the predecessor node for W, which is U. So I am connected to that. Right? So by going to anyone wherever you want to go, you go to the table, follow the predecessor nodes, the link, and then you can create your path back. Okay, and sometimes it is possible that, I had a very nice clean example that every time I found a unique node with the least cost. Sometimes you may find 2 nodes with the least cost. In that case, you can pick anyone arbitrarily. Anyone you like, you can just pick. Questions? Yeah?
So what if there's a scenario where, let's say the cost from X to Z is actually 6?
X to Z, this is 6.
Yeah, instead of 9, it's 6.
Hmm.
So it's more cost effective to go up to X and then Z, right?
Yep.
So how do we determine that? Because as you can see, the link from U to W is more cost effective than U to X. So the algorithm should prefer W than X, right?
Okay, but the thing is, when you when you go through the iterations, you will actually pick up that, if you initially start with a 6 here instead of 9, we can try this. Let's go ahead. This one is 6 instead, right? So initialization, no change, right? It will stay like that. In the next step, you would still pick W, and again there will be no change in this case either. Okay, this row will still be the same. Next you're going to pick U. Next you're going to pick X, and you're going to put X here. Now what you're going to calculate is, all right, for V, so this is done, this is done. For V, previously the cost was 7, and now I can go by 6. So I have 6 comma W here. Oh, hang on, 6, this was already done in step number 2, right? So that's not, sorry, let me change this. We are talking about X here. Yeah. So we have added X. I think it's better to do it this way, so I don't get confused. Okay, so now I have added X. Let's see. The cost of going to X is 5. There is no link between X and V, so this is going to stay as 6 comma W. How about Y? Previous cost was 11, going via X, this is 5 plus 7, which is 12, which is more. So again, no change here. So this will be W. Previously the cost of Z was infinity, so now 5 plus 6 is 11. I'm going to write 11x here. Okay. Now I'm going to pick the smallest one, which is this guy. So instead of 14x, this is just, let me erase everything. Instead of 14x, this is 11x, and this is 6. Okay so far? So now pick the smallest, which is V. V gets added here. So from V to Y. So the cost of V, this is 6. And then from here to Y, 6 plus 4 is 10. So this will stay as 10 comma V. And then from V to Z, there is no link. So there will not be any change. It will still stay as 11 comma X. Fine. Now I will pick V and put it here. I'm sorry, Y, and now Y will be added. So let's see now. Now the cost of going to Y is 10. And then there is link 2. 10 plus 2 is 12. In this case, it will stay as 11 comma X. You're not going to update the cost because any other questions? All right. So in that case, so this was our Dijkstra's algorithm, which is a global one. And the other one that is, which is decentralized and every node computes on its own. This one is based on something called the Bellman-Ford algorithm, and we are not really going into the algorithm itself. I just want to give you the intuition about how this particular algorithm works. In the way this algorithm works is I compute something and I give it to my neighbors. My neighbors compute their own things, they tell me. And we compare this in an iterative way, and at some point we will converge and we will be done. But the goal, the key of this is something called the Bellman-Ford equation. And I just want you may have seen it in other contexts, but let me give you what this means. What it says is, let's say dx of y is the cost of the least cost path from x and y. The way I can find this is, let's say I consider all my neighbors. Okay? I consider all my neighbors. I check what is the direct cost of going to my neighbor, and from my neighbor, what is the cost of going to y. I just pick the smallest one. So I have 5 neighbors, let's say 3 neighbors, right? I check what is the cost of going to each one of my 3 neighbors. And from there, what is the cost of going to the destination? Let's see this in a visualized way, so that will hopefully be easier, right? Let's say Singapore, right? I want to go to somewhere where, let's say, we don't have a direct connection. Usually Singapore has direct flights, let's say, to most places in the world, but some of the places where we don't have are actually in South America. Okay? Let's say I want to go to Brazil. I want to find the shortest path to Brazil, but there is no direct path to Rio. However, I have 3 options. Maybe I can go to, if I fly KLM, I can go to Amsterdam. Or I can go via Dubai or Abu Dhabi or something like that. Let's say Dubai. Or let's say I go via US. This is CISCO, San Francisco. These guys have flights there. Okay? So this one is DA of Rio. This is DD of Rio. I'm just using the alphabet from their names. And this is DS of Rio. And I have direct connections from Singapore to these 3 places. This is the cost of Singapore to Amsterdam. This is the cost of Singapore to Dubai. Singapore to San Francisco. So in order to find the best path to go to Rio, I see if I add all of these things up, both of them, and I just pick the minimum one, that will give me the least cost path. And actually it doesn't matter whether this follows many other hops or not. This is the total cost of going to Rio from San Francisco, Dubai and Amsterdam. I don't care if you have to go through 3 hops, 4 hops or 5 hops. This is the total cost. This is the total cost. This is the total cost. So the total cost of going from San Francisco to Rio plus the cost of going from Singapore to San Francisco. The total cost of going from Dubai to Rio plus the cost of Singapore to Dubai. The total cost of Amsterdam to Rio plus the cost of Singapore to Amsterdam. Of these 3, which is the minimum? That's your best path of going to Rio from Singapore. Okay, so that's basically the whole idea. And the way this algorithm works is your neighbors have to tell you this cost. And you already know the cost of this link because that is your link. So your neighbors tell you these costs, you know these costs, and then you compute. And you can do it in an iterative way. If you're interested, you can look up distance vectors. But this is just basically the intuition. And here was one more example, to show what this is. Okay, so that's sort of our discussion on the network layer. So maybe what we do is we will stop here, and then we will do tutorial number 2. That's wrong. Yeah. Okay. All right. So problem 1 is about go back N, and it says consider the go back N protocol with a sender window of size 4. So that means the sender can send 4 packets at a time. And a sequence number range of 1024. By the way, in this example, the sequence number range of 1024 has no meaning, right? It's just there to confuse you maybe. Okay? And then it says, suppose at time t, the next in order packet that the receiver is expecting has a sequence number of k. Assume that the medium or the channel or the link does not reorder messages. So if you send packet 1, then packet 2, packet 1 will always reach before packet 2. Okay? Things go in sequence. Then we want to answer the following questions. Question A says, what are the possible set of sequence numbers inside the sender's window at time t? This problem is basically to illustrate to you that, when you have a protocol, I am a sender, what's happening at the receiver, I have no idea, except that I get some acknowledgements once in a while. Similarly, the sender just gets some packets and sends some acknowledgements. But just by looking at what you have sent and what you have received, you cannot have a completely accurate picture or an exact picture of what is happening at the other side. You can get a rough view, but you cannot get an exact view of what is happening. That's really what I want to illustrate here. Okay? So it says, what are the possible sets of sequence numbers inside the sender's window at time t? Let's start with that. All right. So this is basically it. Let's start our count at 1. So we can send packets 1, 2, 3, 4, 5, like this. 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. And at the receiver also we can do the same. We have packets 1, 2, 3, 5, 6, 7, 8, 9, 10, and so on. Okay? So let's just say this is K. Okay? I could have done something, but I think having numbers would make it easier. So let's say this is K plus 1, this is K plus 2, this is K plus 3, this is K plus 4, K plus 5. Let me write the same thing again here. So this will be K minus 1, K minus 2, K minus 3, K minus 4, K minus 5, K minus 6. K minus 3, K minus 2, K minus 1. Okay. I just arbitrarily picked 10 to be K. I could have drawn the diagram in terms of K also, but it's just easier to visualize sometimes. All right. So now what the problem tells me is that at some point in time t, the next in order packet that the receiver is expecting has a sequence number of k. So basically, this is what the receiver is expecting. Right? Receiver wants k now. And this is a go back n. So we know that acknowledgements are cumulative. All right. So it says, what are the possible sets of sequence numbers at the sender's window at time t? So basically, I want to see what is the sender's window now. So let me ask you a question. Could the window be like this? Starting at k plus 4. What do you think? No. Why? Because if it is expecting k, the best it could have done is send an acknowledgement for k minus 1. Right? It's expecting k. So we know for sure it has not sent an acknowledgement for k. It has also not sent k plus 1. It has also not sent k plus 2. The max it has sent is k minus 1. Let's say, very good, this ACK has actually reached the sender. In that case, my window will begin at k. How much? 4. K, k plus 1, k plus 2, k plus 3. This is the most I can have my window towards the right. I cannot have this either. My window cannot start at k plus 1 because acknowledgement for k hasn't been sent yet. Okay? I cannot start at k plus 2 either. I cannot start at k plus 1 either. But it is possible that if I was lucky, maybe k minus 1 acknowledgement has been received. So my window will begin at k and go all the way up to k plus 3. That's one possibility. It is possible that, the acknowledgement for k minus 1 was sent, but there is no guarantee that it has been received. Right? In that case, my window could be this. It's possible. Right? Maybe all the acknowledgements till k minus 2 have been received, but not beyond that. In that case, my window will be k minus 1 to k plus 2. However, it is also possible that this particular acknowledgement was never received. In that case, my window will start at k minus 2 and go up here. How about k minus 3? Am I sure that the acknowledgement has been received? We don't know yet. Maybe, maybe not. If it has not been received, then my window starts at k minus 3 and goes up to k. How about this guy, k minus 4? I cannot actually be completely sure whether this acknowledgement has been received or not. So it is also possible that my window is starting at k minus 4 and goes up to k. Now you may ask about this guy. How about k minus 5? Is it possible that this acknowledgement has not been reached? If this acknowledgement was, has not been reached, not been received, my window would have been starting at k minus 5 and go up to k minus 2, or starts at 5, goes up to 8. If that was the case, I could not have sent k minus 1. Right? Imagine acknowledgement for k minus 5 has not been received. If that was the case, my window would at least start at k minus 5. And the maximum my window could go is k minus 2. Then k minus 1 would not have been transmitted. But the problem tells me that it's expecting k, so that means k minus 1 definitely has been received. So k minus 1 definitely has been transmitted. So I am sure that this ACK has definitely gone through. Because if this ACK hadn't gone through, k minus 1 would not have been transmitted. So I know I'm definitely sure that on this side the boundary is k minus 4. It is possible that this ACK has not been received. That's okay. None of these ACKs have been received. That's okay. So I have sent k minus 4, k minus 3, k minus 2, k minus 1. The packets have been received here, just that the ACKs have not gone back. That's possible in this scenario. That would say I would still get k minus 1. But in that case, maybe my window is this, maybe my window is this, maybe my window is this, and so on. So the most I can go on my, left-hand side is k minus 4. My window cannot start at k minus 5, k minus 6. But on this side, the best thing that could have happened is the acknowledgement for k minus 1 has gone back. In that case, my window will start at k and go up to k plus 3. So all these solid windows that I've drawn here, any of them can be possible. My sender could be at any one of these windows. We don't. If I'm the receiver, I cannot be exactly sure which one, but I know it's one of these 5 possibilities. So, in this case, what I say is, window. In the range k minus 4 to k and size 4. So this is the starting point, either k minus 4 or k minus 3 or k minus 2 or k minus 1 or k, and then on the other side will be plus 4. Okay. If you want to do it in terms of n, so you just replace 4 by n, we have k minus n to k, and the window is of size n. So this is the beginning point is in this range. Was it okay? Any questions? All right. Now part B says, what are the possible values? Let it come up. So it says, what are the possible values of the ACK field in the possible messages that are currently propagating back at time t? So that we have already done here actually. What we can see here is, oh, come on. All right. So what we can see from here is, it is possible that the ACK for k minus 1 is currently on its way back, has not reached. It is possible that the ACK for k minus 2 is currently going back, has not reached. ACK for k minus 3 is going back, has not reached. ACK for k minus 4 is going back and has not reached. But I am sure ACK for k minus 5 has definitely reached. And anything in this side They definitely have reached. So it's only 4 ACKs which might be on their way back at this time. They may have already reached, they may not have reached, but these are only these 4. What is the language we are using? Yes. K minus 4, K minus 3, K minus 2, K minus 1. Or if you want, it's like K minus 4 to K minus n. Or if you want in terms of n, K minus. Good. Okay, let's give our projector time to switch back, and then we'll go to question number 2. All right, that was quicker. All right, in this problem, we will compare go back n, selective repeat, and TCP, and no delayed acknowledgement. So every TCP packet will be acknowledged immediately. All right. Assume that timeout values for the 3 protocols are sufficiently long such that 5 consecutive data segments and their corresponding ACKs can be received, if not lost in the channel, by the receiving host and the sending host respectively. So timeout value is long enough, right? And suppose host A sends 5 data segments or packets to host B, and then the second segment or packet is lost. So I'm sending 5, the second one is lost. In the end, all 5 data segments have been correctly received. So there'll be some timeout or whatever loss recovery is there, and then you do retransmissions, but at the end of the day, all packets will be correctly received. Suppose that the initial window size of TCP is 5. Again, usually TCP starts at 1. We have seen they do a slow start, but let's say it's starting at 5. And then the TCP receiver keeps out of order packets in its memory. Then part A says how many segments has host A sent in total, and how many ACKs has host B sent in total, and what are their sequence numbers. Answer this for all the 3 protocols. Okay, so we'll see how many ACKs, how many packets, and their exact sequence numbers. And it says how many segments, part B says if the timeout value is much longer than RTT, 5 RTT, then which protocol successfully delivers all 5 segments in the shortest time interval? So let's draw all 3 of these. So let's say I have go back n. This is selective repeat, and I have TCP. A, B, A, B, A, B. And time is going in this direction. Okay? All right. So what it says is we are sending 5 packets. The second packet is lost. So packet 1, packet 2, 3, 4, 5. Right? So these are the first 5 packets that will be sent by go back n, and this will say acknowledgement for 1. Packet 2 has not been received. Now go back n gets packet 3. In go back n we do cumulative acknowledgements to say how much we have received in sequence so far. So this is still going to say 1, right? Because 2 hasn't been received, 3 has been received. So far I have received up to 1 in sequence. Packet 4 is received, acknowledgement will still say 1. Packet 5 is received, acknowledgement will still say 1. Right? So now, let's say there's some timeout value. Once the timeout occurs, in go back n, everything in the window will be retransmitted. 1 doesn't need to be retransmitted because we got the acknowledgement for 1, but we will send 2, we will send 3, we will send 4, we will send 5. And this time there is no loss, so we get an acknowledgement saying 2, get an acknowledgement saying 3, 4, and 5. Okay. So then we can see total packets 1, 2, 3, 4, 5, 6, 7, 8, 9. How many acts did we get? 1, 2, 3, 4, 5, 6, 7, 8. What are the packet sequence numbers? We sent 1, 2, 3, 4, 5, then 2, 3, 4, 5. Right? And then act numbers were 1, 1, 1, 1, 2, 3, 4, 5. Questions? Okay. Let's go to selective repeat, right? So the initial story is the same. So we send 1, that goes through, 2 is lost, 3 goes through, 4 goes through, 5 goes through. Right? So now in selective repeat, each packet is acknowledged individually. There is no cumulative acknowledgement. So acknowledgement for packet 1 will say 1. This is going to say 3. This is going to say 4. This is going to say 5. No acknowledgement for 2. So we're going to keep waiting. And then there's a timeout. And when there's a timeout, in selective repeat, we only send the packet for which we lost the time, the timer expired. So here we will just send 2. And the acknowledgement for this will come back just saying 2. Right? So in this case, total packets 1, 2, 3, 4, 5 plus 1, 6. Total acts 4 plus 1, 5. Packet sequence numbers 1, 2, 3, 4, 5 and then followed by 2. And then the act numbers is 1, 3, 4, 5, 2. Good? Questions? All right. Let's go to TCP. Again, same thing. 1 goes through, 2 doesn't. 3, 4, 5. 1 is acknowledged, but in TCP, the acknowledgement doesn't say 1. It's cumulative ACK, but it's going to say give me 2, right? It says the next one. I have received 1, I'm looking for 2. Packet number 3 is received. It's not in sequence. I will do cumulative acknowledgement. So far I have received 1. So I'm going to say, give me 2. Packet 4 is received, not in sequence, give me 2. Packet 5, not in sequence, give me 2. At this time, this was the first ACK. For 2. Then this is duplicate, duplicate, duplicate. 3 duplicate ACKs. What happens? Fast retransmit. So we retransmit packet 2. And the problem tells you that we are keeping out of sequence packets in the memory of the receiver. So now when packet 2 receives, it has already got 3, 4 and 5 here. So how much we have received in sequence? Till 5. 2 fills the gap. So we have received till 5 correctly. So this guy is going to go back and say, give me 6. Right? So the total packets in this case is 1, 2, 3, 4, 5 and then 1 more, which is 6. Total ACKs, 4 ACKs, then 1, 5. Packet sequence numbers, 1, 2, 3, 4, 5, and then I'm going to squeeze in a 2 here. Okay. And then if you look at the acknowledgement number, it is 2, 2, 2, 2, 6. Right? So that's sort of the first part. And then part B says if the timeout values for all the 3 protocols are much longer than 5 RTTs, so many RTTs longer. So I made the timeout pretty long. Which of these 3 protocols successfully delivers in the shortest time interval? You can see that for part B, the answer is TCP, right? Because it doesn't do a timeout. Timeout needs much longer time. We do a fast retransmit and then get done quickly with TCP. This is part B. Questions? Okay, in that case, I think this is a good time, 5:30, so we stop here. And when we come back Wednesday, we will start data link layer. All right.